we talk about parent function, do some review on the graphs of these parent functions. The critical movements is what I use. You can also think of it as a coordinate. But what are parent functions? These are your pure functions before you've transformed them. You haven't stretched or shrunk them in any way. You haven't deflected them over any axis. You have not translated them right or left, up or down. We use these parent functions and their respective movements to help me draw graphs of functions that have been transformed. So let's take a look at 9 different functions here. First one is a linear function y equals x. We're going to refer to these concepts of critical movements, and what critical movements are is they are right, left, up, and down movements from some start point that helps me generate the other points of the graph. So I'll be referring to a start point for all of these functions and then their respective critical movements. All right, here's we have our first one, y equals x. Y equals mx plus b. B is 0, slope is 1. So if I were to generate the graph of this thing, and I just pick my own x values and stick them into a table, if I put a -2 in for x, I get a -2 for y, and a -1, I get a -1, and a 1, I get a 1, and so on. So on the left-hand side here, we have coordinates. And then those coordinates, we're going to think of them as critical movements. And the negative for the x values, a negative is equal to a left movement. A positive is equal to a right movement. In the y coordinates, a negative is equal to a down. And positive is equal to an up movement. So when you see these coordinates on the right here, this -2, -2, that means left 2, down 2, left 1, down 1, right 1, up 1, right 2, up 2. And all of this happens from your start point. That's critical. So here's the graph that we get. Linear function. Those are the points that we go through. And there's our first parent function. So now if I were to take this graph and I would add, let's say, 4 to this equation, y equals x plus 4, well, what that does is it gives me a new start point of 0, 4. And from that start point, I would still work and apply these critical movements. Left 2, down 2, left 1, down 1, and so on. If I were to put a coefficient in front of x, like a 4, then that coefficient is affecting your up and down movements. It's stretching them by a factor of 4, so all your y values would be multiplied by 4, and so on. So that's how we use critical movements and stretch factors and shrinks and reflections. But this is just to focus on what are the critical movements of parent functions. Our next one, absolute value function, has a start point of 0, 0. Absolute value function actually is a piecewise function, and it is generated from y equals x if x is greater than or equal to 0, and y is equal to the opposite of x if x is less than 0. So I have two linears, one of the positive slope, one of the negative slope, creating these two V, or these two lines that create a V. So it looked like this. That's the first one. And there's our second. This would be the graph of y equals x. This is the graph of y equals negative x with those respective domains. So when we put them together, we get this V shape, and here are the critical movements for it. Left 2, up 2. Again, how did I get those? If you put a -2 in for the absolute value of x, you get a +2. Put a -1, you get a +1, and so on. Critical movements for absolute value functions. Quadratic functions, y equals x squares. They have a vertex. Also, we will refer to that. That's our start point at 0, 0. If I were to graph this guy, we would generate a parabola And how we got those points, if we were to look at negative 2, 4, and then negative 1, 1, and then positive 1, 1, and positive 2, 4, those are the values that help me create that graph. Here's that parent function. Square root function. This is the reciprocal of a quadratic. And what does it look like? Looks like this. Can't have negatives underneath that root, so we're using positives only. So a right 1 movement generates an up 1 movement, and a right 4 is an up 2. So we have our parent starting out at 0, 0, then we have a 1, 1, then a 4, 2, and then a 9, 3. Next, a cubic function. If you put these movements in, left 2, down 8, left 1, down 1, right 1, up 1, we would create that graph. So we have a left 2, down 8, left 1, right 1, right 2, and again, a starting point of 0, 0. How about a cube root function? Again, starting point of 0, 0. Notice that we flip the x and y's here. This is an inverse of the cubic function. I think I might have said last time that this quadratic and the square roots were reciprocals. I meant to say that they are inverses. So if we take a look at this graph, now this software doesn't actually graph cubics correctly, so we have to put them in 2 separate equations. But left 8 down 2, left 1 down 1, right 1 up 1, and right 8 up 2. Reciprocal. So now we get into the types of functions that have asymptotes. And let's talk real quick asymptotes. Asymptotes are those lines that our graph is going to approach. Some functions, as in this one, have both vertical and horizontal asymptotes. How do we determine them? Vertical asymptotes, we look in the denominator. We see what values of x would make equal to 0. And those are the values that create our vertical asymptote lines. Horizontally, we look at the degrees of the function in the numerator and the denominator. If the degree in the denominator is bigger, we have a horizontal asymptote of 0. If the degrees in the numerator and the denominator are the same, we can get a generic slope of a slant asymptote by looking at the Lie coefficients. If the degree in the numerator is bigger than the degree in the denominator, we will have no horizontal asymptotes. So this is a reciprocal function. Notice now that instead of having a legitimate starting point, we have these things called imaginary start points. That means our graph is not going to go through 0, 0. But what we do with 0, 0 is we use it to base our movements. So our movements are coming from there. If I were to create the graph for this thing, we see we get these, whoops. Oh, what's going on? There we go. We get these branches, create this hyperbola. And we have 2 main critical movements, and those would be these 2 here. But considering this negative 10 left fin movement down a tenth, and then a left 1 down 1, and a right 1 up 1, and a right 10 up a tenth, we're just going to go with the ones we know. That's not what I was looking for. There we go. See if we can get the tenth here. No. So those are the movements of a reciprocal function and the graph that it generates. Again, going off an imaginary start point. Notice the graph doesn't go through 0, 0. Exponential functions. I'm using an example of y equal 2 to the x Generically speaking, we have y equals some base value b to the x. And again, this one has an imaginary start point. And that is because there is no way for me to get a value of y equals 0. It doesn't matter what I put in for x, negatives, 0, positives, I can never create y equals 0. That's why we generate this horizontal asymptote at y equals 0. This one, in particular, looks like that. And all exponential functions will take on this shape. Now, they will always cross the y-axis at 0 unless they've been translated. Their next movement, though, is dependent on the base value. So these critical movements that we have in this table are specific to y equal 2x. Generically speaking, though, we could have this as my movements. Left one, and then down, well, that's going to change. If I have a base of 10, I'd be down 1 over 10. So I'd have a 1 over b movement for my y. And then this will always be 0, 1. And then my next one will always be 1b. Again, b being the base value of that function. There's your 0, 1. This one has a 1, 2. Logarithmic function, I think this is our last one. Another one that has an asymptote, and another one that has an imaginary start point. I don't go through 0, 0. This is the inverse function of an exponential. And this is an example of a log base 10. This is a common log. And so I can't ever get a value of x equals 0 here. So we have an asymptote at x equals 0. I'm not going to generate the graph for this one because it actually doesn't create the correct graph, so we're just going to use the coordinates here. So if I put in a 1/10 in for x, I'd have a -1, or a down 1 movement. If I put a right 1 movement, I'd have a 0 up and down movement. And if I put in a right 10 or b, I go up 1. So this one comes like a branch and then gets real close to that asymptote, continues to get close to it, and then makes that turn and goes out. And again, for t-table purposes, generically speaking, if we went 1 over b, we're going to get -1 for my movement. Right 1 up 0. Right b up 1. Generate the logarithmic graph or whatever that base value happens to be. I believe we got it.